whispers of angel that falls in love. Do you remember the sound of the ocean waves? Breaking a long time after high. Believing in magic can make you strong. Tell everyone that this is a place where you belong. Everything looks shiny, there's someday in your life. Close your eyes to find yourself in wonderful world. Everything feels like your fantasy. The night in your life. Close your eyes to find yourself in this tick-time life. Do you remember that you're the wind on you? Soft as and whispers of angel that falls in love. Do you remember the sound of the ocean waves? Breaking a long time after high. Believing in magic can make you strong. Tell everyone that this is a place where you belong. Everything looks shiny, there's someday in your life. Close your eyes to find yourself in wonderful world. Everything feels like your fantasy. The night in your life. Close your eyes to find yourself in this tick-time life.
Hi everybody. Welcome back to Chem 161. We've got, what do we got today? We got Lewis structures, it looks like. And a lab that's due tonight. I mistakenly said it was due last night, and then somebody corrected me. Thank you for that. Tonight, though, I did check. I did go and look to make sure it's actually due tonight. And it is, so make sure you get lab number 4 due, turned in by the deadline tonight. Some people are still asking me questions in the Discord. which is totally fine. Like, I'm happy to answer those. I just might not see some of these. Like, I'm actually looking at this now, and like there's a whole discussion going on. And I'm like, oh crap, I got to go back and look at that. But of course, I'm streaming right now, so I can't do that. So yeah, if you have any questions, like hop in there, talk about stuff. Like that's what it's for, right? What else do we have? There is a quiz for Unit 3. That's due next week. I'll start putting that on the thing down here, the doodly do. I don't know, whatever you want to call that little word bubble that is coming out of my face on the screen right now. So you'll see that next week. And there will be a quiz for Unit 4. There will not be a quiz for Unit 5 because Unit 5 is just so short. I put all the questions for Chapter 5 in the exams themselves. But we're right on track to get through all the content. So let's just get right into it, huh? All right. So this guy who is significantly less insane than Pauling. I just like to make fun of Pauling. Like, he did a lot of great stuff, but he did go nuts. Pauling did like this crazy, like, oh, everybody should have all this vitamin C, and basically stop believing in science. I don't know exactly what happened to him, but G.N. Lewis was another chemist back in the day that was doing research on various compounds, and he was trying to find patterns between what he observed and the properties of various elements. And he came up with this sort of like cube diagram that you can see in here, where he represented valence electrons as the corners of cubes. And he said, well, okay, if I can get all 8 of these corners full by combining 2 elements together, that should make a stable ionic compound, such as NaCl would have 1 valence electron and chlorine would have 7. We've actually shown that electron transfer when we showed Lonnie's lab. I showed you what sodium chloride looks like in its formation, and then we showed how we could move 1 electron from sodium to chlorine to fill both of their S and P subshells. So what we have done over the years is we have devised these cubic symbols into a more simplistic sort of diagram that looks like this. And so this is called a Lewis symbol. So we're going to be using Lewis symbols to describe valence electrons in all of our elements and ions and so on and so forth from here on out. Because it's a really convenient way to describe how bonding occurs. This might be one of the most important skills to develop. Fortunately, it starts out really easy. Drawing the Lewis symbol of any element is a 2-step process. 1, draw the symbol of the element. And then 2, draw dots. 1 dot for each valence electron, going around the 4 sides of the symbol. So let's do an example. This is sodium. We need to count the valence electrons of sodium. Well, I've indicated them in blue right here. So, because sodium has only 1 electron in its 3s subshell, and that's the only subshell populating n equals 3, it has 1 valence electron. So that means that we're going to draw 1 dot. So here's our Lewis structure. Draw the symbol for sodium. There you go. Draw a dot for each valence electron. There's only 1. Boink. There you go. That's it. This is the easiest thing you'll do in this class. However, it is also extremely important. Now, what happens if you have a bunch of electrons in the valence shell? Because there's 4 sides, right? How do we draw them around all 4 sides? Can I put as many as I want? Not quite. Remember, electrons repel. So there is a method to this madness when we are putting in more than, say, 4 electrons. So if I write out the electron configuration for an element like oxygen, I would get something like this. What are the valence electrons? They're in the highest n, so that's these. there are 6 valence electrons. So I'm going to draw 6 dots. Okay, let's do the 2 steps. Step 1, draw the atomic symbol. There you go. Step 2, draw a dot for each valence electron. Now, if I start doing stuff like this, what's going to happen is that these 2 that are paired together will repel, right? So I don't want to pair electrons until I absolutely have to. So the rule is that when you're putting dots around electrons, put 1 dot on each side first. And then we're going to start pairing them. Now, something interesting that you'll notice. If I draw this diagram out, and I were to fill this in for oxygen, here, we'll put oxygen's 1s down here. So those are core, we don't really care about them. But for my 6 valence electrons, you'll notice that it matches up with the electron configuration diagram that we've been working with all along, right? Look at that. So what we're doing is we're taking the electron diagram and more or less making it up into a picture. Now, there are some circumstances where these 2 will not match yet. Okay? We're going to encounter those in chapter 5. Or I should say, we're going to encounter them now, but we're going to just sort of ignore it. And then we're going to explain what's going on in chapter 5, because there is a phenomenon that's going on here that we haven't explained yet. Okay? But for the most part, our diagram is going to have the same number of pairs and unpaireds as the electron configuration diagram, with maybe one exception. All right, and there's my dots. Now, when you're drawing your Lewis structure, it does not matter which side the paired electrons are in and which side the unpaired electrons are in. For example, if you did this, and I drew in my valence electrons like that, so that, oops, that's 7. Sorry, I went too many. And I don't know why that last one kind of glitched out there. If I did this instead, that's totally okay, as long as I have 2 pairs and 2 unpaired. What would not be okay would be to do something like this. Because that would imply, oh, I have this empty space here, but all my electrons are packed together. So something would get repelled and fill in that space to give you the correct structure. Okay, so you can't do this. That's why we do 1 at a time until we have one in every position. And then we'll do pairing. So what I want you to do is I want you to draw the Lewis symbol for each of these elements by putting dots around it. So, for example, for carbon, write out its electron configuration, count the number of valence electrons, and then draw its symbol. There you go. Remember that for carbon, or not remember for carbon. Remember that there are some exceptions to, hey, this doesn't look like our electron configuration diagram. Which ones are 2s? And we'll get to that in chapter 5, so don't worry. Carbon in the 4a column is kind of the weird, oh, this kind of doesn't work. But everything else, it does work, for the most part. So, do this for the remaining ones. Remember that ions change the number of valence electrons, so be mindful of how many electrons you are using. Okay? So do this for lithium and sulfur and so on and so forth. And when you've drawn all the Lewis structures, don't try and draw them in the chat, because that's not possible. Just say done or something like that, and then we'll move on. How are we doing? 1 or 2 more minutes? All right, let's go over the answers here. So I'm going to write out the electron configurations for each of these. So for lithium, we've got 1s2, 2s1. So that's just one valence electron. And so we'll just draw it. Boop. Now, be careful that when you do lithium, you don't do something like this and go, oh, there's my valence electron. Like, make sure that, like, your valence electron that you're working with is distinct from the little dot on I, because it's really easy to mistake that. So if you draw your dot, like, way too high on accident, and it's something like this, so like lithium, and then here's your dot, that could be misinterpreted. So be careful. I think lithium is the only one you really have to worry about that with for. All right, so sulfur here is, so sulfur is neon, 3s2, 3p4. So that's 6 valence electrons. So sulfur is going to look like this. 1, 2, 3, 4, 5, 6. You can put those on any side that you want as long as you have 2 paireds and 2 unpaireds. So there's chlorine. It's got 7. So we'll draw chlorine. 1, 2, 3, 4, 5, 6, 7. There you go. And then aluminum is that. And aluminum has 3 dots around it. There you go. Now, aluminum also kind of doesn't really resemble what its electron configuration would look like. You would expect, oh, a paired and an unpaired, but that's not what we draw. And again, we'll discuss why that is later. All right, so B+, so for boron, I would have that. But if I make it plus, I got to get rid of the first highest energy valence electron. So that's this one right here. Goodbye. There we go. So that's what that looks like. So now there are only 2 valence electrons. And that would look like this. So B with 2 dots around it. One thing I didn't say is that when we have ions, the convention is to put the ion in square brackets and then put the charge in the top right corner. So put your dots inside the brackets, and that'll be the correct way to show that. Now, if you forget the brackets, it won't get marked wrong. But the reason that we do that is just to put the charge somewhere that is easy to recognize, and we just put it in the corner of the brackets. What do we got for Br? So Br is krypton. Oops, not krypton, argon. Four S2, 3D10, 4P5. Now it's got a minus on it, so I need to up this 5 to a 6. Oop, there we go. And then what's my valence shell? It's just those 2. So that's 8 valence electrons. So Br would have 8 dots around it. And then because it's Br minus, we would do that. And there you go. And then finally for xenon, xenon is krypton 5s2, 4d10, 5, not 4. I said 5 and wrote 4. 5p6. There's my valence shell. That's also 8. So xenon is just going to look like this. 1, 2, 3, 4, 5, 6, 7, 8. There you go. Those are our Lewis structures. Any questions, let me know. All right, so now we know how to draw Lewis symbols for elements and for ions. Didn't we already do this? Hold on. I swear we did the Lonnie's lab thing already. Now I'm trying to find it, and I can't find it in my slides here. I could be mixing it up with a different class. Yeah, I don't see it. Interesting. Okay. Wait a second. Hold on. We did this in Unit 3, right? Yeah, I thought so. Okay. So we don't need to see this again. My slides just have it in there twice. And I remember the slide where we showed it moving from one electron orbital to the other. Yeah, okay. Yeah, that's the same video. I don't know why it's in there twice. Oh well, we'll just skip it. So what's going on here is that when we do a reaction to form ionic compounds, we're going to move valence electrons around such that I get everybody to have a full S and P subshell. So for sodium, remember that it was neon 3s1. I'm going to take that 3s1 electron, which is this guy right here. I'm going to just pass him over to chlorine, which has this and would become that. And in doing so, everyone has a full S and P subshell. What I'm going to do is, instead of calling this a full S and P subshell in the valence shell every single time, we're going to give this a new term. Because there are 8 electrons in the valence shell when this happens, we're going to just start calling it this. Octet. So the goal for our atoms is to get an octet, because that will be a full S and P subshell in the valence shell. If we can do that, we get a stable result. Now, stability is relative. There are still going to be octets that are reactive, of course. Oh, excuse me. But they will be more stable than the elements or ions that they started as. So when we make ionic bonds, the first thing that we have to do is form ions. And so that means that we're going to pass electrons back and forth until everything has an octet. And then once we do that, we will have 2 entities that have charges on them. This is what it'll look like after we've passed electrons back and forth. And these will then be attracted to each other. Now, in order for this to happen, we need something that passes electrons from itself. So we need to have a metal involved. And then we need something to give the electrons to. That's where the nonmetal comes in. So the metals are always going to be the things that pass away their electrons, and the nonmetals are going to be the acceptors of the electrons. All right, so what I want you to do now is for each of these pairs of elements, first draw the Lewis structure, then try and pass around electrons, and see if you can get the ionic equation that way. So we know what the ions form from these because we did chapter 3 earlier. But what we can do now is we can see this in terms of valence electrons being moved around. So for instance, if I had this, in order to get everything to have an octet, I could move this electron over there. This would have an octet, and that would have an octet. So the formula is KBr. So instead of writing out all of your electrons, this time do it with dots. Move around dots until everything has an octet. And we'll go over the answers in just a little bit. How are we doing? Any questions? Let me know. Say hi. Hello. Hello. Yeah. Okay. Maya says hi. All right, let's go over the answers. Just gonna keep saying hi in the background here while I go over the answers here. So we got calcium and oxygen here. So that's what that looks like. If I can move my electrons to give everyone an octet, this will work great. So I'm going to put one right here. And this one will go over here to pair with this guy. And so that means this has an octet, this has an octet, then what our result is calcium oxide. I'm going to run out of space for the rest of these, so let me get this going here. There we go. Oops, I don't want the crop tool, I want that. So magnesium, I will do pink, that's fine. That's what magnesium looks like. And then we got chlorine. Like that. And I can move an electron to pair this way so that this has an octet. But I still have this extra electron here, and I have to do something with that. And so what ends up being the option is, well, if I had a second chlorine, I could pass that right on over to it. And then that would have an octet, and this would have an octet. So the formula we would get then would be MgCl2, because I used one magnesium and two chlorine to do this. So this is just another way of visualizing ionic bonds. So now we'll look at sodium and nitrogen. We'll put it up here. I could pass this one over. That's great. But I need to have two more to pass electrons over in order to fulfill the octet rule for sodium here. Or not sodium, but nitrogen. So this would be Na3N. And then for aluminum oxide here, we could easily predict the formula to be Al2O3. Let's show how that happens with valence electrons. So there's aluminum. There's oxygen. We're going to pass 2 over. So that one's done. But now I need another oxygen available to collect this last one. It's just that that won't fill the octet for oxygen, so I'm going to need another aluminum here. We'll pass this one over. Now I need a third oxygen. And so I'll pass the remaining 2 over here and over here. Sorry, I covered up one of my electrons there. So now everything is good. Al2O3. All right. So that should be no problem to get the formulas that we already knew how to create based on what charges we make for these elements from what we studied in Unit 3. And what do we do from here? Well, that's ionic compounds. Ionic compounds are just transferring electrons. Can we apply this idea to covalent bonds and try and understand how electrons are shared? Absolutely. With covalent compounds, it turns out the same thing is true. We want electrons to be arranged in such a way that everyone has octets, but we can't pass electrons back and forth because if I do this, this one's good, but this one's not. Also, if I was trying to make F2, fluorine has such a high electronegativity, it would never want to give away an electron, it only wants to take them, right? So instead of doing this transfer, what we're going to do is we're going to share electrons. And that's done like this. I don't know why the F's disappeared. Let me try that. Where did they go? Oh no. My animation broke. Hold on. Hold on just a second. There we go. Wow, I don't know what was happening there. PowerPoint was just being silly. Alright, so I have now moved my two fluorines together, and this is what I'm going to do. So let me take... Oops, I didn't mean to do that. I also didn't mean to pause them, so you can go back together. There you go. Wow, my computer is like falling apart in PowerPoint. All right, so here's what I'm going to do. I'm going to circle the octet around fluorine here. And then I'm going to circle the octet around this fluorine here. And notice what I'm doing. I am double counting the electrons in the middle by simply putting them in the region where my orbitals overlap, right? So if I do this, these two electrons are shared. Now I can only share lone electrons. I can't share a pair of electrons because that would be too many electrons in that middle region. So when we share two electrons, we make a bond. And our bonds will be represented by these lines here. So this is what's called a covalent bond. Specifically, when I share two individual electrons, one from each atom, I create a single bond. Now, I can share more than one single electron. I could share multiple unpaired electrons to get multiple bonds. So we're going to do that in just a second here. So again, whenever you make a covalent bond, each atom contributes one unpaired electron, and you need two total electrons to make a bond. Then when I go and check to see, oh, okay, did everything satisfy the octet rule? When I go like this and circle it, I'm going to count each line as 2. So I have 1, 2, 3, 4, 5, 6, 7, 8. Because the electrons are shared, I get to count them twice. 8 electrons are on this, so that's good. That has a full S&P subshell. I'll do the same thing over here. 1, 2, 3, 4, 5, 6, 7, 8. That one's good too. So in other words, we're just cheating. We're double counting electrons by putting them in a space that is shared. So this is what covalent means. All right. We'll talk about multiple bonds in a little bit. So this is our formal introduction to the octet rule. Everything that we've done is trying to get 8 valence electrons around it. And this is formally known as the octet rule. So the octet rule is just, if you are an element in these groups, 1 through 8A, you form enough bonds so that you get 8 valence electrons. Now, depending on what your partner is, if your partner is a metal, you'll accept electrons from them. If your partner's a non-metal, you'll share. Unless you're the metal, then you give the electrons. So metals and non-metals transfer electrons. Pairs of non-metals will share electrons. What do pairs of metals do? It turns out they do something totally different. They make mixtures. We're not going to cover metallic bonding in this class, just these 2 types of bonding. So now that we've seen this, we could do the Lewis structure for virtually anything, really. So let's try this by doing CF4 and H2O. So first I'm going to draw out the pieces, not with a highlighter, but there we go. So this is what carbon would look like. And this is what fluorine would look like. And I have 4 of these fluorines. Now, what these Lewis structures end up looking like, oops, that's not where I wanted to put that. When we start thinking about for this simple exercise that we're doing, is they kind of look like football plays or diagrams, where you just have arrows going all over the damn place. So there's CF4. How would I make bonds to other things? Now remember, I have to pair unpaired electrons together to make bonds. So if I did this, that would be a bond. If I did this, this would also be a bond. But that would make F2, right? So that's not going to make CF4. So there's really only one option here. And that is to take all of my unpaireds on carbon and pair them with 1 unpaired each on each fluorine. Now I have to tidy up because this is not a Lewis structure, so you can't draw this as your structure, but it can help you think about it. And so the result that we would get here looks like this. There you go, that would be CF4. So now what I want you to do is try and draw the Lewis structure for H2O, following the strategy that I just showed you. Okay? I'll give you 2 minutes to do that, and then I'll draw the answer on the board and we can compare. Now, if you're drawing your structure and you're thinking, well, what the heck do I do with hydrogen? It's only got 1 electron to begin with. Hydrogen's kind of special in that it only needs to pair its electron to be happy. So just try and pair hydrogen's electrons and satisfy the octet rule for oxygen. I'm going to clear what I have on my screen here really quickly. Boop. And hopefully you got this for water. Now, if you did yours at like an angle or something like that, any other orientation other than a straight line, totally fine. So if you did water like this, because you've seen me do it this way before, that's good too. We don't care about geometry just yet. I'm drawing everything at right angles for simplicity. We're going to care about geometry a little bit later on in the chapter. Now, so the formal rule that we use for hydrogen is hydrogen follows the duet rule. Hydrogen only wants 2 electrons because the nearest noble gas to hydrogen is helium, and helium only has 2 electrons. So if hydrogen can get a full 1s shell, it's content with that. We can never get an octet around hydrogen, so don't worry about hydrogen only having 2 electrons. That is the correct configuration. Okay, that's how we draw very basic Lewis structures. So when we come back from the break, we're going to look at more complex examples by forming multiple bonds. So we're going to explore double and triple bonds, and then we're going to do the Lewis structure of anything. Why is hydrogen like that? Yeah, it's only got 1 proton, so it can't attract 7 extra electrons to it. It can barely have 2. But that's exactly the reason. Its Z effective is too tiny. All right, so we'll put the slides here. I'm going to put the break time timer up because we're going to take a break. And I will see you in 10 minutes after some more Final Fantasy 13-2 music. So, see you in a bit. I never started the timer. Hold on, let me fix that.
Heart of chaos cannot take, paradoxes must break. This is the path I must take. My destiny may change your fate. The pain my heart feels is my strength. Collide and people fade, seeking gates through timelines. We've all prayed, let's fix the past, trade it now to see smiling faces. This hope, heart of chaos cannot take, paradoxes must break. This is the path I must take. My destiny may change your fate. The pain my heart feels is my strength. Worlds collide and people fade, seeking gates through timelines. We all pray, let's fix the past, trade it now to see smiling faces. This hope, heart of chaos cannot take, paradoxes must break. This is the path I must take. My destiny may change your fate. The future to come is what we've made.
Alright, we are back. I fixed the timer. Apologies for that, not starting, I didn't hit the button. Alright, so let's talk about making multiple bonds in a molecule. So sometimes you need to pair more than one electron because you just have more than one unpaired electron available. So, for example, if I have oxygen like this, I could bond to something and then something else, but there is no rule that says I can't just bond to the same atom twice if there are two positions available. So if I if I share both of my electrons with oxygen, there's a space for both of them in oxygen's octet around it. It only has 6. I could let it have 2 more from the other oxygen to share them together. So if I do this, then the result that we get looks like this. Now I'm going to replace those 4 dots with 2 lines to represent a double bond. So a double bond places 2 pairs of 2 electrons, which means that within this double bond right here are 4 shared electrons. Now, if you're thinking, well, that's a lot of electrons to cram in like a tiny space between 2 atoms. Yeah, that's a good thought to have at this point. And in fact, we're going to cram even more in there. We're going to make a triple bond which has 6 electrons. Now, there is a geometric property to this that allows it to work. We're going to show that geometric property in Chapter 5. But for now, this is legal. You are allowed to share more than a pair of electrons between 2 atoms. In fact, you can share up to 3. So if I did this for N2, I would get a triple bond. So let's actually draw that really quickly over here. Sorry, there's a motorcycle driving by. You probably hear that. Sadly, it's not my motorcycles. Boo-hoo. Alright, so here's my nitrogen. I'm going to pair these 2 together. And I'm going to put this one over here, and I'm going to put this one over here. And when I do that, my structure would look like this. And that would satisfy the Octet Rule too, by making a triple bond. So here's my triple bond. And this would be 6 shared electrons. So that's allowed too. Now, if I try to do this with carbon, I had an issue. And that issue is I can do these 3, but if I try and do this one, I'd have to go all the way around, right? Well, I can't make a bond that goes around. It has to go in straight lines, and I'd bonk into the nucleus if I did that. So the most that I can do is 3. And so I can do a triple bond with carbon. It's just that what I would end up with is something that looks like this. And then these would need to pair to some other thing. Whatever that ends up being. And actually, that's where we're going to start going with this, is we're going to start making these giant molecules that I can connect however the heck I want to, using my unpaired electrons. So the maximum number of bonds that you can make covalently between any 2 atoms is 3. We're not going to make a quadruple bond due to geometric concerns that we'll talk about again in Chapter 5. Now, as our Lewis structures get more complicated and complex, it's going to become harder and harder and harder to use this piecemeal strategy of, oh, I'm going to just connect the dots to whatever is available. Because I'm going to start getting molecules that are just so big and ginormous that you have too many pieces. It's going to become like a 1,000-piece jigsaw puzzle where all the pieces are blue. Like, who knows where to start even? Like, you'd have to literally just go through every possibility. So, that's too difficult for a more complex molecule. So we're going to prescribe a strategy that will work to help us make the Lewis structure of virtually any molecule that we want to work with. So we're going to use this 5-step plan to make Lewis structures for anything. When you follow the 5-step plan, very important, you have to do the steps in order. And if you skip a step because there was nothing to do for that step, you cannot return and go do it again. Okay? You have to do these steps in the order that they're presented. And you can't skip forward and you can't return. All right, so step 1 for any molecule that you're going to be working with is to count valence electrons. Step 2 is to draw a framework. I'm going to put all these instructions back. I'm just saying the 5 steps before we do them. Step 3 is to use electrons to fill octets around outer atoms, and then fill remaining electrons on the inner atom, and then make double bonds or triple bonds if you have to. Okay, that's the gist of this. Count your electrons, hook everything together in a framework, do the outer atoms first for valence electrons, put everything else on the central atom, and then make multiple bonds if you have to. So what we're going to do, I'm going to go back to these steps. I'm going to cover them back up, and we're going to go over here, and we're going to apply this to a practice molecule. I'm trying to find Photoshop. It's way over here. I don't know why I couldn't. There we go. All right, so the first thing we're going to do is we're going to grab a sample molecule. And the molecule that I'm going to use for a sample is CO2. So step 1 is count valence electrons. How do you count valence electrons in molecules? Well, we would add up each of the individual atoms' valence electrons and then sum the total together. How many valence electrons do each of these atoms bring you? Well, we could be doing this over and over. But that's going to get super tedious real quick. Has anyone discovered a pattern to the number of valence electrons an atom has and its position on the periodic table? Because there is one, and it's going to make all of this obsolete. We could just go straight to 4. What is that pattern? Anyone know? I'll give you a hint. There's a reason I just put the periodic table on the screen. Well, let's look at carbon. This is the atom that we're looking at right now, right? Carbon has 4 valence electrons. What group is it in? Oh, look, 14. What about oxygen? If I hide this, and I count the number of valence electrons that oxygen has, we would get these, which would be 6, right? Well, let's look at what group oxygen's in. Boop. Oh, look at that. It's in group 16. So, if we just look at what group our atoms are in, and we use the ones digit, that's the number of valence electrons it has. So if I ask you how many valence electrons boron had, well, you just go, oh, it's in group 13, the ones digit is 3. Boron has 3 valence electrons. How many valence electrons does iodine have? Oh, it's in 17. The ones digit is 7. It has 7 valence electrons. And this works for every element in the first 2 columns and these last 6 columns, except for helium. Helium only has 2 valence electrons because it's element number 2. But for every other element in this main block, or the A group elements that we would call them if we were either Canadian or using an old periodic table that had 1 through 8A, we could count valence electrons that way. We're never going to count valence electrons for the transition metals because we always get the number 2. And it doesn't really make much sense. And we're not going to use them for covalent bonding anyway because they don't form covalent bonds 90% of the time. So now we could just take all of the quantum mechanics we learned in electron configurations and just shove them in the garbage where they belong, right? We just use the periodic table and count the number of valence electrons really easily. So that's what we're going to do. Carbon has 4 valence electrons, and each oxygen has 6, and there are 2 oxygens. So the total number of valence electrons in this structure would be 6 times 2 plus 4 is 16. Okay, so we've counted our valence electrons for our structure. If we had an anion, we would have to modify that. So if we had like CO2 minus, we'd have to add an extra electron. If we had CO2 plus, we would remove an electron. Step 2, we're going to make a framework. And my directions kind of fell off the screen here. When you do the framework, you're going to take the most electronegative atoms and put them on the outside, and put the most positive atom in the middle. Sometimes the formula gives you a hint at the structure. The second element is usually the central atom if hydrogen is in front. If there isn't a hydrogen, then the first atom is the one that's in the front. Hydrogen can never be the central atom because it can't form more than one bond. So since carbon is listed first here, I'm going to put carbon down, and then I'm going to put my oxygens around it. I'm going to try and be as symmetrical as possible. If I had a third one, then what I would have done is I would have done something like this. But if I only have 2, I'm going to just put them opposite from each other. Now, this isn't a framework until I've connected everything together. So I'm going to make bonds. So bond, bond. Remember that each bond needs 2 electrons. So up here in my count, I'm going to remove 2 electrons from the bank. My bank of valence electrons. So there's my structure. That's my framework. I've made a basic skeleton of what the molecule will look like. Now for step 3, we're going to put electrons around the outside atoms first. You have to do the outside atoms first. If you do something else, you'll get the wrong answer. Now, when you put the electrons in, you just care about getting them to an octet. So you can fill them in however you want to. So I'm going to go like this. 1, 2, 3, 4, 5, 6. That cost me 6 electrons. But that oxygen now has an octet. Remember that the bond here counts as 2 for that oxygen too. Now I'm going to use the rest of the electrons to do that over here. And now I'm out of electrons. So now we'll go on to step 4. Which is to place any remaining electrons on the central atom. We don't have any extra electrons. If we had them, they would go on the central atom. If we had enough that it made more than an octet, you still put them on the central atom. You'll see why later. Finally, if we have any atoms that don't have an octet, particularly the central atom, we're going to make multiple bonds so that everything has an octet. So step 5 gets us to here where we're looking at who has octet. So this oxygen does have an octet. The left oxygen does. But this carbon only has 4 electrons around it. Remember, these bonds are 2 electrons shared with both ends of the bond. So I'm missing 4 electrons on carbon. So in order to fix this, I need to take 2 electrons from one side, whoop, and transfer them into a bond. So I went like this to put those in the wood spot. Now if I look at this, I'll notice that I'm only missing 2 electrons now. So by doing that, it gets closer, and this oxygen over here still has an octet. So if I do the same thing over here again, whoop, now I have an octet for carbon too. So the multiple bonds forming comes in only if you need to. You only make multiple bonds if you have no other option to give everyone an octet. So in this manner, we've done the Lewis structure for CO2. All right, let's do another one. Let's do ammonia. Oops, I'm not clicked on the thing here. All right. Now, I'm not going to go back and show the rules, but you should probably remember the rules from this. So, oops, hold on. So let's do ammonia. Let's do the Lewis structure for ammonia. So step 1 was to count valence electrons. So how many valence electrons should I have for this? Go ahead and count the valence electrons in ammonia and type your answer in the chat. Tell me what you should get. Use the periodic table. Don't do electron configurations anymore. We've used electron configurations to get us to where we need to be. Now we don't need them anymore, which is not what you want to hear, I know. But we'll save time. Hopefully you're typing to me from the past and you have said, oh, well, there's 5 in nitrogen, and each hydrogen has 1, and there are 3 of them, and so that you got this. Step 2 is to make our framework. The atom in the middle goes in the center. Or, I'm sorry, the atom is listed first, is what I meant to say. And then I'm going to put everything else around it symmetrically as possible. And then I'm going to connect things together. So that used up 2, 4, 6 electrons. Then we're going to do outer octets. Well, they're all hydrogen, so I don't need to do anything. So that step's done. We'll move on to the next step. I'll put the remaining electrons on the inner central atom. And then I'll make multiple bonds if I have to, but everything has an octet and all the hydrogens have a duet. So this is the correct Lewis structure for ammonia. For drawing some Lewis structures, you're going to notice that you finish the structure early before you get to step 4 or step 5 or whatever. So if at any point you have an octet everywhere or all your hydrogens have duets, stop immediately and save that as the structure. Okay, so it is possible to finish the structure and then the remaining steps you do nothing. You take no action. All right, so my slides walk through doing this, but we just did these examples. And then we did ammonia. So you've seen 2 of these. I'm going to do one more, and then I'm going to have you do the other 4. So let's do SO3 real quick. All right, so let me get rid of all this. All right, so let's look at SO3. We're going to count valence electrons. Oops, I don't know if that's in the way or not, so we'll do that. So sulfur is in group 6. Oxygen is also in group 6. There are 3 of these. 3 times 6 plus 6 is 24. So that's step 1. Step 2 is we're going to draw the framework. Oops, I drew the bonds a little too early there. We're going to make 1, 2, 3 connections. That's 6 electrons. So this becomes 18. Then I'm going to fill in octets on the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used all my electrons, so there's nothing to put on the inner octets. I need to make multiple bonds because my sulfur does not have an octet. So I'm going to just pick one and do that. And there you go. That's the structure. Now, could I have picked any other bond? Could I make a double bond to something else? Yeah, you just rotate it around, right? Because it's symmetrical. Now, that's what I'm going to tell you for now. In the next section, we're going to learn that, oh, if you have choices, you have an interesting situation. But for now, this is a good enough structure for SO3. So now that you've seen that, draw the Lewis structure of these remaining things here. So do carbonate, do ammonium, PCl3, chlorite, and then NO+. Okay. Remember that the charges modify the number of electrons that you get to play with. So if you had something like this, SO3 2 minus, that's 2 extra electrons. So you would add 2 down here. Okay. If you had positive, you would deduct an electron or whatever. So draw the Lewis structures for those. I will go over the answers with you in about 5 or so minutes. Good luck. We're all counting on you. how are we doing? If you have questions, let me know. All right, one more minute. We'll go over the answers together. All right, so let's go back here. All right, let's do the next one. We'll do carbonate. You're going to notice that carbonate and SO3 look very similar to each other, and that is actually intended. All right, so here's carbonate. We're going to count the electrons. So carbon gives you 4. Each oxygen gives you 6. I don't know why I did that with the parentheses there. There are 3 of them. And then I have to modify my total number of electrons. If I make the molecule have a -2 charge, that's because I gave it 2 electrons. So my total number of electrons here is 24. So there's my skeleton, my blueprint here. I made 3 bonds, so that's -6 electrons, so now I have 18. Put the remaining ones around the outside, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That was all of them. I do need to make a double bond somewhere because my carbon in the middle does not have an octet. There are no electrons that I can put there, so I can't do step 4. So I'm going to just pick this one. And there you go. There's my structure. We'll put the ionic charge on the outside of the structure. I put it a little higher, but my count got in the way. So there's the structure for CO3 2-. All right, let's do ammonium. So nitrogen is 5. Each hydrogen is 1. I've got 4 of them. And then I have this positive charge, which means I have to subtract an electron. Because to make something positively charged, you have to remove an electron to do that. So that's 8 electrons. And you're going to notice that when you make the framework for this, that uses all your electrons, and you're done. So this is the structure. You get to step 2 and it's done. Sometimes that happens. All right, let's do... Oh, I ran out of space, so we'll go up here again. We don't need the directions anymore. I think you have the directions memorized. If not, you can pause the video and get them back. PCl3, a phosphorus is 5. 3 chlorines is 7 each. So that's 21 plus 5 is 26. So PCl, Cl, Cl. 2, 4, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I used 18 to do that. There are 2 left over. So when I get to step 4, which is put stuff on the inner atom, I'm going to put 2 on there. And then I'll check for octets, and everything does have an octet. So this is the correct structure. When we do chlorite, each chlorine is worth 7. There are 2 oxygens, and each oxygen is worth 6. And I have this minus, which gives me an extra electron. So I have 6 and 2 is 12, 13, 20 electrons to work with. We'll do something like that. 2, 4 to connect. I gotta put the rest around the outside. 2, 4, 6, 8, 10, 12 to do that. So I have 4 left over now. Where do the remaining 4 go? Well, they go on the central atom, so I'm going to put them right here and here. That's all of them. Does everything have an octet? Sure does. So we're all set. All right, and then finally, we'll do NO+. So this is 5 plus 6 minus 1 is 10. So we got nitrogen and oxygen. We'll just connect them together. Now, when I have a choice of where to put my electrons, they're both technically outer atoms, but I have written the N first. So I'm going to put my electrons on the more electronegative atom first. So we'll do that. So that was 6. And then I'll do that with the last 2. Now I don't have anywhere near an octet on this oxygen, so I need to remove a pair to do that, and remove a pair to do that. I'm going to just move this one to the other end so it looks good. And there's my structure. All right, now some of these structures that I have drawn for these examples turned out great, and we're not going to modify them later. But in the next few sections, what we're going to do is we're going to refine this technique and add other stipulations onto it. And we're going to come back and modify some of these structures, such as this one. It turns out that there's a better way to draw this structure, even though this follows all of our rules so far. Whereas PCl3 up here is totally fine as is. So we're going to explore that in a little bit more detail in this next section. So this will be the last thing that we cover today because we're running out of time here. And so this is, hey, sometimes the octet rule doesn't quite work. Why are you allowed to do this, and when can you do this? So the first exception to the octet rule, we've already talked about, it's hydrogen. Hydrogen is too tiny. It has Z effective of 1, and that's barely enough to hold on to its 1 electron or 2 when you pair it. So hydrogen is so small, all it needs is 2 electrons, so that's the duet rule. So hydrogen follows the duet rule. Helium doesn't make covalent bonds. Lithium and beryllium make ionic bonds, so we don't have to worry about those. Small atoms tend to not follow the octet rule. Once you get to carbon, it's big enough that it can handle having that many electrons. Now, there is an element along the way between hydrogen to carbon that does make covalent bonds, but is kind of tiny and has weird circumstances going on with it, and that's boron. We'll talk about boron in a little bit. The next exception occurs when you have an odd number of electrons. For example, we did NO+, and that was 10 electrons. But what if you have NO? I could never satisfy the octet rule with an odd number of electrons, right? Because the octet rule would require an even number. I will either have 1 too many or 1 too few. Almost all of the time it will be 1 too few. What do you do if you have an odd number of electrons? Well, you follow the rules that we set out as best as you can, and then the lone electron is going to end up on the central atom in almost all cases, because that'll just be where you stick your leftover electrons. So if you end up with 1 single electron because you have an odd-numbered species, that's okay. That extra lone electron will be on the central atom, whatever that ends up being. Now, something that's interesting is that lone electrons tend to be extremely reactive. So, you may have heard the term free radical. So what these are all radicals. So a radical is an unpaired electron that did not find a bond. And what free radicals try to do is they either try and collect another electron, or they find another unpaired electron somewhere else to form a bond. So if I had 2 of these NO2s, they might bond to each other. And in fact, they would. NO2 often dimerizes in solution. So this sometimes happens, particularly with nitrogen. And you just draw the best Lewis structure you can with the extra unpaired electrons on the central atom. Then we can talk about boron. Here's a common compound for boron, BF3, and you'll notice that, well, this is weird. Why are there only 6 electrons around boron? Shouldn't I make a double bond? And the answer is, if I were to make a double bond with fluorine, remembering that fluorine is the most electronegative atom on the periodic table, what I would have to do is I would have to take a pair of electrons and force fluorine to share it to do this. And it turns out that fluorine really doesn't like doing that. Fluorine wants to get all the electrons for itself because it's the most electronegative, right? So making fluorine do this, it turns out, is not okay. And there will be another metric that we're going to discuss on Monday that will show us, what Lewis structures are okay and what Lewis structures are not, called formal charges. We'll talk about that later. The formal charges also support that this structure is just bad, and that this one is the best one. Now, even though boron only has 6 electrons around it, it's not super stable. And in fact, something that boron will do is it will try and find something that is willing to give it 2 electrons to make a bond. And this is a sort of a weird reaction that's special. And it shows that covalent bonding is more than just, I have some electron, we'll pair them. In fact, what you can do is have something that has 0 electrons and accept 2 electrons from it to make a bond. So in fact, I can do this. I can give both of these paired electrons to make this bond. And this is kind of unique. Very few elements are capable of doing this because they don't have an electron deficiency. So this is kind of a unique thing that boron does, but metals also do this too. And so whenever we have chemistry where I can make covalent compounds with transition metals, this happens. So you're going to see this in third-year chemistry if you go that far. This happens to be my entire major, so I could talk about what these special bonds are. This specific bond is called a coordinate covalent bond. And it opens up just a ton of new possibilities for covalent chemistry. Naturally, we're going to see it on this slide, and then you're never going to see it again. But boron can do this because it has the availability for, hey, I need 2 electrons. So it can do this with something that has 2 electrons available. You can do this with water. You can do this with a bunch of other things. But it's just a thing that's unique to boron. So if you see boron with only 6 valence electrons, that's pretty common if it's by itself. All right. The last exception that we're going to talk about is when you have just too many electrons around an atom and you get forced to just shove them on the central atom. So this happens for things like PCl5. I haven't drawn the electrons on here. I'll put them in really quickly, though. The term for anything that accepts more than 8 electrons around the central atom is hypervalent. And so this can never happen for second row elements. So anything in period 2, this doesn't happen. But in period 3 elements, this happens all the time. And the reason for this is because when we are putting these electrons into our atom, we're putting them in the valence shell. If we're looking at the n equals 2 valence shell, this is what there's space for. I can put in 8 electrons, and then that's it, we're full. But if I'm looking at the n equals 3 valence shell, I have s, p, and d electrons available. I ran out of space. So I can actually put up to 18 electrons here. So depending on what your central atom is, if it's a second row element, you can only ever have at most 8 electrons around it. So that's at most 4 bonds. But if it's a third row element or lower, you can make more bonds. You can get up to 18 electrons, which means you can have up to 9 bonds. Typically, we only really go up to 6, because at that point, the atoms start to get crowded. There's just so much stuff around the central atom that you can't squeeze it all in there without everything else pushing other things away. In this class, we're going to look at 5 and 6. So these hypervalent molecules can exist, but only for elements in the third row of the periodic table or further down. All right. And so that slide describes that. So what does that mean for when you're drawing a Lewis structure? Well, if you get a Lewis structure, such as, say, this, I'll do this one example, and then we're out of time. We'll start with this slide next time. And you go, oh, I have to put all these fluorines around this iodine. Well, you just do it. That's totally fine, because iodine is below period 2. It's in period 5, right? So as long as it's not in period 2, you can put more than 4 things around it. So first, let's count the valence electrons. We got 7, and then I got 7 for each fluorine times 4. So that's... Oh, not 4. I'm sorry, I miscounted. I added those in my head, and I was like, that's an odd number. That doesn't make sense. There we go. So now I have 42 electrons. So I'm going to put iodine down. I'm going to put fluorines around it. I'm going to try and space them out the best that I can. We'll connect them all. 2, 4, 6, 8, 10. And now I'll put down the remaining 32. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. There's 2 that are left over. We'll put them on the central atom. 32. There you go. That's the structure for IF5. And yes, there is that pair of electrons on that central atom, in addition to the 5 bonds. So that would be 6 different positions, 5 of which are bonds, and 1 is an electron pair. So you can totally do that if and only if your element is period 3 or lower. Period 2 cannot do this. All right, so as a little bit of homework, what I want you to do is try and draw these Lewis structures. We will go over the answers on Monday next week. Next Monday, I'm going to very briefly talk about the lab, because the lab is basically a review lab. I'm going to give you wine, and you're going to analyze its contents using the techniques that you've learned from all the previous labs. And that's pretty much the lab. There's very little else that I can talk about other than having you all do work and then ask me questions about it in Discord as they come up. Like, there's nothing new there. But yeah, so we will continue with this slide next time. Our agenda for next week, which is week 10, this is the last week. This is the last time we'll be meeting online. We're going to finish Unit 4 on probably Tuesday. So we're going to lecture on it on Monday and then Tuesday. And then Unit 5 is very short. I will do hybridization on Wednesday. And that's it. There will be one more quiz for Chapter 4. There will be an exam for the rest of Units 3 up through 4 and 5. And then the final. And then spring break. 2 weeks off before we come back for more in 162. So yeah, we're almost at the end. Which means don't panic. Keep your head in the game. And hang in there, because the end is in sight, thankfully. I'm as exhausted as you guys are. So, have a wonderful weekend. If you have any questions, let me know in the chat. Make sure you get that lab done tonight. It is due. Have a good one, and I'll see you on Monday.